Hello to everyone. Let's begin our second part of the chapter Probabilities with a look around to combination and combinatorics, more generally speaking. Combinatorics are the way to count possibilities in a given random experiment. And the purpose at its appears is being able to count the outcomes of an experiment. So the events and some possibilities that can come out a given experiment. Let's take examples, of course. You've got an object that represents an initial set of possibilities. Okay, that could be considered as outcomes, but let's name them issues for the moment. And after some experiment, there can be some outcomes of the experiment. And the set of the possible outcomes is named the sample space. So with some examples, it will appear clearly. Let's take an object like a coin to play heads or tails. Okay? A coin is an initial set that contains two possible elements that are heads or tails, okay? Or a head and a tail. Let's name them simply H and T. The experiment consists in tossing twice the coin, okay? So you could have two coins in your hand and toss them at the same time, or to toss twice the same coin. It will be exactly the same. The sample space here is not the initial set. The sample space is HH, HT, TH, TT, because you've got two coins, and each coin could lead to one single event, H or T. So there are here four possible pairs of results. The game here in combinatorics is to be able to count the total number of possible outcomes, whatever the experiment and whatever the initial set in the initial object. Another example, roll a die. A die is an initial set of 6 possibilities. Okay, it's a 6-sided die here. So the initial set is 1, 2, 3, 4, 5, 6. If you want to roll 3 times the die, you will obtain 3 results that consist of a certain series of 3 results. Okay, it could be 1, 1, 1, or 1, 1, 2, or 1, 1, 3, and so on, and so on, and so on, until 6, 6, 6, if you want to sort them in the sample space. The question is, how many elements are there in the sample space? And of course, in many situations, you don't have to write all the outcomes of the experiment because it will be too long. In this example, you've got 216 possible outcomes. It is the size of the sample space. So the question is, why 216? And our purpose is to be able to count that without writing them. So let's have a reasoning, a thinking about the possible case, okay, the possible situations and physical situations. If you're playing heads or tails, let's take back to this example and tossing them 3 times here. You have to be able to write an example of outcome. Not all of them, but 1 or 2 or 3 examples, and it will be enough. An example could be tail, tail, head. Okay, it could have been something else. For example, tail, head, tail, or head, tail, tail, and so on. Okay, and let's compare it to a second example. That is going from a deck of 52 playing cards. So the initial set being the deck, it contains 52 elements. I want to take 3 cards at random from this deck. And let's build an example of outcome. It could be the king of spades, the jack of hearts, and the 8 of clubs. Okay, So it's one of the multiple examples that could occur from this experiment. So, are there here different cases? Are these two physical examples different from one another, or do they belong to the same category of examples? You have to note that there are two numbers that will be very important for us. N, the number of available elements in the initial set, and P, the number of elements that you want to take to create your outcomes. So, if you want to establish the fact that these two cases are very different cases, you have to ask to yourself two questions. The first one is about repetition. Is repetition possible in an outcome, yes or not? In the first example, it was obvious that a repetition would occur because if you are tossing 3 times a coin, it will give you the same result at least 2 times. Okay, in our examples, we've got 2 tails, but if not, we would have got 2 heads or 3 tails. Okay, one element has to be repeated. In the second example, you can't have twice the same card. You can't have twice the king of spades. So there is a difference that is very important for us in order to perform the right calculation afterwards. The question of repetition. Then, second question that is as important as the first one is about order. Do you have to take all the possible orders into account in one outcome that would create several outcomes? If you pass points, you have to take the results in the correct order. The result that we built here is TTH. It's not THT. Okay? The two outcomes contain exactly the same elements, but there are different outcomes, and they have to be counted separately. Because each coin gives one result and not one other. In the second example, if you obtain the king of spades and then the jack of hearts, or if you obtain the contrary, it will be counted at the same outcome. In most of playing games with cards, you don't have to take the order into account. All that matters is the cards that you have in your hand. And of course, you can think of different situations. If you count the possible orders, you will obtain more outcomes than if you don't count. Okay? And if you allow repetition, you will obtain more outcomes than if you forbid repetition. So all that thinkings lead to the total number of possible outcomes. So now let's have a closer look on all of that, considering all the possibilities in yes or no to both questions. The first situation is named p-lists. The p-lists consider both repetition and order. Let's take an additional example with an initial set that is just a set of numbers, 1, 2, 3, 4, 5. And you want to take at random 2 numbers from that to form 2 long numbers. So numbers that contain 2 figures. So for instance, you can take the 2 and the 4 to form the number 24, or the 3 and the 3 to form the number 33, and so on. Okay, it's not forbidden here to take twice the 3. Okay, if it was forbidden, or if it were forbidden, it would have been written. So the case is simple, and this time we are allowed and we are able to write down all the possible outcomes. Here there are, from 11 to 55, all the possible numbers of two figures that you can form from the initial set. Our purpose is to know how many there are, okay? And the outcomes here are 25. You've got 25 outcomes. And our goal will be to be able to calculate this result without seeing the outcomes, just from n equals 5 and p equals 2. So let's perform a little analysis of the situation. N equals 5, p equals 2. Was repetition possible? Yes, of course. 11, 22, 33, 44, 55 are possible outcomes. Then, is the order to be taken into account? Yes, because 1, 2 is not 2, 1. Okay? There are two different figures, or two different numbers, sorry. 12 is not 21. So you have to take the different orders into account. If both answers are yes, you are in case of p-lists. So your outcomes are named p-lists. And here, more precisely, two lists, because there are lists of two figures. Now, how could we calculate the number of p-lists in every possible situation with whatever value of n and of p? Let's draw a choice tree. In order to choose the first number, we've got 5 possibilities. 1, 2, 3, 4, or 5. And then for the second figure, we've got again 5 possibilities. So we can understand that sorted like that, we've got 25 possibilities in the end. 25 terminations on the tree. And you can read from the top to the bottom 11, 12, 13, 14, 15, 21, 22, 23, and so on. So why 25 in the end? Because 5 times 5. 5 groups of 5 branches. Okay? And that's just 5 squared. N to the power of p. So let's sum up. A definition of p-lists. A p-list is an ordered list formed with p elements taken from a set with possible repetition. So you've got in this definition order and repetition. Result, the number of possible p-lists from a set of n elements is n to the power of p. So you can say n power of p if you want. Let's put this first example and this first result into a table, okay, that we take all the possibilities into account. So if both answers are yes, you are in p-list and you have to calculate n power of p. And then let's perform 3 examples talking about p-lists. In the next slide, we've got to develop examples. Okay, how many ways for placing 2 objects into 3 drawers? If you want to place 2 objects into 3 drawers, you have to take at random 1 drawer for the first object and 1 other for the second one. Your initial set is a set of 3 drawers. N equals 3. You want to make a choice twice. So you want to choose a drawer twice. Not obviously the same, but what are possible outcomes? So as you can notice, I'm displaying a scheme here that shows the initial set and then on the right, the set of outcomes. It will be very important for you in order to make any mistake. So a possibility is to take or to put the object A in the first drawer and the object B in the third one. So now you can ask your questions. Question of order: is this the same as the first? Okay. Is this the same arrangement of objects? No, of course. If you do a permutations between the two drawers, it's another outcome, another possibility to place your two objects. So you have to take the order into account. Then the question of repetition. Are you allowed to repeat the choice of a drawer? Is this possible? Yes, of course, because it's not forbidden. So, the both answers are yes, you are in case of p-lists. The number of ways for placing two objects is 3 power of 2, or 3 squared, which is 9. Next question, how many numbers of 4 figures only contain the figures 1, 2, 3? So, for example, 1213. If you want to build such numbers, you have to take 4 figures in a set that contains 3 figures. Okay, you each time you just can choose only 1, 2, or 3. So your available elements are 1, 2, 3. You want to take 4 of them, and so you can see that you will have at least one repetition. So examples of outcomes. 2312. Okay, the question of order, if I'm permuting two elements in that outcome, is this the same outcome? Obviously not. It's not. So you have to take the order into account. Is a repetition possible? Yes, we just said that the repetition was unavoidable. You are in p-lists, and the number of outcomes is 3 power of 4. That is 81. If you are courageous, you can write them all, okay, from 1111 to 3333. Last question, how many words of 5 letters taken from A, B, E, M, I, R, O? You just have to take 5 letters from this initial set. And the most important here, as always, the questions of repetition and order. So let's take an example. Buy more. This is a word of 5 letters taken from the initial set. So if you are permutating 2 letters, buy is it another word? Yes. So you have to take the order into account. Is the repetition possible? Yes, because it's not forbidden. So you're still in p-lists, and the number of such words is 7 power of 5, which is 16,807. So by the way, the result is mostly much more than expected, okay? You don't have to trust your confidence if you want to estimate the future result, okay? It's impossible. So you have to trust your method and to trust formulas. Next case, named permutations. Let's take back our initial set 1, 2, 3, 4, 5, and then from 2 long numbers with different figures. So this time, we are not allowed to take twice the same figure. What are the outcomes in this case? Almost the same as earlier, but 11, 22, 33, 44, and 55 are forbidden. So these outcomes are named permutations. Permutations are a part of p-lists. So there are less permutations than p-lists. Here you've got 20 permutations. Our results are these ones. N equals 5, P equals 2. The repetition is not allowed, and the order has still to be taken into account. 12 is not 21. Let's define them, or draw a choice tree, sorry. So for the first figure, you had 5 different possibilities. But for the second one, you only have 4 possibilities, okay? So you know by seeing a choice tree that there are 5 groups of 4 branches, and then 5 times 4 equals 20 terminations on the tree. So why 5? Because n equals 5 at the beginning. And why 4? Because your tree gets 2 levels. And there are 2 levels on the tree because p equals 2. So you have to multiply decreasing integers from 5. 5 times 4, and you stop there because p equals 2. If you want to form numbers of 3 different figures, you have to add a third level at a tree with 3 branches at every of the 24 terminations. And then the number of global terminations of your new tree will be 5 times 4 times 3. So still a decreasing multiplication of integers. So definition, a permutation is an ordered list formed with p different elements taken from a set. Order, but different. No repetition. The number of possible permutations of p elements taken from a set of n elements is, and then a formula appears that you have to consider, but your calculator will know it, so you don't have to use it manually. So the first thing is that there is a notation for permutations, is a p with a subscript with n and an exponent with p. So that's just a symbol, okay? The formula is the following. You have to calculate the factorial of n divided by the factorial of n minus p. So let's stop here a little. What is the factorial of a number? So you have to look at its notation. So if you want the factorial of 5, for example, it's 5 times 4 times 3 times 2 times 1. Okay, you have to calculate the product of every integers from your number to 1 on a decreasing way. So in our example, n equals 5. So you've got on top of the fraction 5 times 4 times 3 times 2 times 1. And below you've got n minus p. So 5 minus 2 equals 3. Factorial of 3 is 3 times 2 times 1. Okay, and if you simplify your fraction, you will see 3, 2, and 1 vanish from the top and the bottom. And that remains will be 5 times 4. So this is the general formula that helps us to calculate any permutation with any value of n and of p. In our table, its location is order yes and repetition no. So you have here to calculate permutations. So how do you ask for permutations directly in your calculator? With a Casio, you have to enter the value of n first, and then go to option, okay, the key option on the top left of your calculator. You have to choose on the screen probabilities, and then NPR, because permutations, okay, it's a P of permutations. When it's chosen, you have to enter the value of P. So for example, you can ask 5 on PR 2, and the result will be 20. With the Texas, it's almost the same. You have to enter n. You go in mat proba and take NPR or arrangement. In French, permutations are named arrangements. You enter P and then enter. So now let's perform 3 examples with permutations. How many pairs representative assistants from a group of 25 students? So you have to vote for 2 students. One will be a representative of the group, and the second one will be his assistant, his or her assistant. Your initial set is the set of 25 students. Okay, you have to choose 2 of them. And what is a possible outcome? So, for instance, the student 4 and the student 12. Is this choice a different choice? In fact, yes, because one is elected to be a representative and the other to be an assistant. So if you make the choice 4-12, it's not the same as the choice 12-4. You have to take the order into account. Is this possible? Okay, so to vote twice for the same student? No, of course, you have to choose 2 people. So repetition is forbidden, and you are in case of permutations and not p-lists. So this time, you've got permutations 25, 2. If you had to build a tree, you would see that there are 25 possibilities on the first level and 24 possibilities to choose the second student on the second level of the tree. So your number of permutations is 25 times 24, but you just have to ask your calculator 25 permutations 2, and the result is 600. And yes, indeed, 25 times 24 equals 600. Now, second question, number of ways to pile 3 blocks, taking them among 10 blocks of different colors. So you've got an initial set of 10 blocks. So I just wrote 4 of them here in French. So red, green, blue, yellow, okay, and so on. 3, not 3, but 10 colors. You have to take 3 of them. And what are possible outcomes? So let's name them in French. Rouge, vert, jaune. Is this one another outcome or the same? So just have a look. Each time you're taking exactly the same element as in another outcome, and you're just asking to yourself if it's another outcome. Yes, it's another way to pile the 3 blocks because the order of the 3 colors counts into the results. But is it possible to choose vert, rouge, rouge? No, because there is only 1 red in the initial set. So you're in case of permutations, and the number of outcome is P10-3. That means if you want to calculate it by hand, 10 times 9 times 8, the result will be 720. And you can ask your calculator, 10 permutation 3 results 720. Now, last question. How many words with 5 different letters in A, B, E, M, I, R, O? So your initial set is as earlier A, B, E, M, I, R, O, and you want to take 5 letters, but this time you forbid repetition. You want 5 different letters. So this word is a possibility. This word with a permutation of 2 letters is again a possibility, and it's different. But this word is forbidden. You can't take it into account. So you're not in p-lists. You don't have to calculate, or you mustn't calculate 7 power of 5, but you must calculate 7 permutation 5. The result will be 2520. The former result with p-lists was 16,807. So it's far bigger. If you forbid repetition, you have a little number of outcomes compared to the former one. Now let's see a third case that is named combinations. This time you've got your initial set, but you just want to take two different figures. You don't want to form numbers, so this time it's just as if you want to take two different objects into your initial set and just note the objects that have been taken without any order. Now the outcomes are these ones, and there are 10 outcomes, whereas earlier there were 20 permutations. So combinations can be seen as a part of permutations. Okay. Our results here are these ones. The answers of both questions are no. If you forbid repetition and if you don't want to take the orders into account, you are in case of combinations. So, a comment here, a choice tree won't help us. A choice tree implies order because you've got a first level and then a second level in the tree. So it would make you think about the situation with a certain order, and we won't think of the situation with an order. So let's compare combinations and permutations to be more direct. Combinations are 1, 2, 1, 3, 1, 4, 1, 5. That's what you can get in your hand. Okay? 2, 3, 2, 4, and so on. If you would take the order into account, you would see that from the combination 1, 2, you can obtain the list 1, 2, or the list 2, 1. These are the two permutations from the combination 1, 2. So let's recall that permutations take the order into account. Okay, you've got two permutations for this combination, but you've got two permutations for each combination of the list. And you are just going back to your 20 permutations that you've seen earlier. Okay, so if you want the number of combinations, you have to divide the number of permutations by something. Here it will be by 2. So the formula of combinations looks like the formula of permutations. Definition: a combination is a set, no order, formed with p different, no repetition, elements taken from a set. The number of possible combinations of p elements taken from a set of n elements is, this time with the letter C for combination, C and p, which is still the factorial of n on top and the factorial of n minus p at the bottom, but multiplied by the factorial of p. This is, in fact, the factorial of p that is the difference between both formulas. With the former example, we had to divide by 2 the number of permutations to obtain the number of combinations, because 2 was the factorial of p. The factorial of 2 equals 2, because it's 2 times 1. But if p equals 3, the factorial of p will be 6 and not 3, because 3 times 2 times 1. So whatever, your calculator contains this formula in its memory, so it's not a problem. The combinations are located here in the table. And now let's give a comment for the empty cell in the table. It's out of schedule, okay? It won't be applied here, and it's never been applied for the first or second year of study. It's a case where order is not to be taken into account and repetition is still possible. So it's a gamma formula which uses combinations, but not exactly the same way. So you don't have to consider that. You will always be placed in the 3 cases that appear in this table: p-list, permutations, or combinations. Your calculators are able, as for permutations, to give you combinations. You just have to choose NCR and not NPR on occasion, or to choose combinaison in a Texas instead of arrangement. Let's perform 3 examples of combinations. How many couples of representatives from a group of 25 students? This time you want to vote for a couple of students. There is no order because you don't want to give some characteristic of each student, okay? There have just to be 2 students. Your initial set is the set of 25 students. You have to take 2 students. Of course, the 2 outcomes that appear here are the same outcome. You don't have to count it twice, so you don't have. Okay, I'm just putting it off the set of outcomes. And of course, this third choice is impossible. So no order, no repetition. You have to calculate combinations. C25-2. So in details, C25-2 is 25 times 24 divided by 2. So this time it won't be 600, but 300. Second example, how many different hands of 8 cards from a deck of 32 playing cards? So you have to choose 8 cards from a deck of 32. So let's name the cards like that, but there is no importance. So a possible outcome is to take the king of clubs, in French, roi de trèfle, the 8 of spades, in French, huit de pique, and so on. So 8 cards. If you obtained the 8 before the king, it would be the same result. You would have the same game in your hand. Okay, so you don't have to count it twice. And of course, you can't have twice the same card. So deck of playing cards lead to combinations almost every time. Okay. The number of outcomes is here. Combinations 32, 8. That is a big number. More than 10 million possibilities. So that's the number of possible different games you could have in your hand. Last question, how many draws of 6 different integers taking them between 1 and 49? So you can consider you're playing a lottery game, and you have to choose 6 numbers from 1 to 49. A possibility is this one, 13, 2, 7, 21, 9, 43. If I am doing a permutation of 2 elements, 13, 7, 2, 21, 9, 43, it's the same results. Okay, it's a same way to play this game. So it's not an other outcome. And we have the possibility to take the 2 twice? No, it's not. Okay, of course. So you are in combination situation, and then you have to calculate C49.6, and the result is almost 14 millions. Okay, that means that you've got 1 chance in 14 millions to win this game. Now, let's talk about the last part of this part of the chapter, combinations in a partition. So it's a very important part that could lead to complicated examples, but in case of combinations, it's not so complicated, and it will be important for the next semester as well. So I have to talk to you about this case. So let's see with an example what I want to do here. Why or would be there a partition? If you're taking as initial set your alphabet, n equals 26, you've got 26 letters, maybe you would be interested in the fact that what you could take out this set would be a vowel or a consonant. So I have to here do a partition in my alphabet between the consonant n1 equals 20 and the vowels n2 equals 6. This time, if I'm taking some elements from this set, for example 3 elements, and drawing them simultaneously, that means we are in case of combinations, I could be interested in the number of consonants and the number of vowels I could obtain among the 3 letters. The set of outcomes, our sample space, omega, can be parted again as the initial set, not in consonants from one side and vowels to the other side, but in subsets that contain only 3 consonants, or 2 consonants and 1 vowel, that is a different possible situation, or 1 consonant and 2 vowels, or 3 vowels. So maybe it could be interesting in some situations to separate subsets inside omega in the end of the game. And then we have a possibility to calculate separately the number of elements of the subset A, the number of elements of B, the number of C, and the number of D. At the same time, we are able to calculate the total number of elements of omega, of course. It will be combinations 26, 3, regardless of the fact that a letter is a vowel or a consonant. But if you want to enter in details in the number of consonants and vowels that you could obtain, you have the possibility to calculate combinations for consonants and combinations for vowels separately. And in the end, you are allowed to multiply both combinations. So the cardinal number of omega is C26.3, that is 2600. Okay, but in A, well, the cardinal number of A is C23 times C60. That means that you have to choose 3 consonants in the subset of consonants, there are 20 consonants, and no vowel in the subset of 6 vowels. After having multiplied them, the result is 1140. You can notice that C60 equals 1. You were not obliged to multiply by 6 or C60, okay? Because choosing nothing is like doing nothing, okay? And you're just multiplying your first result by 1. So C23 itself equals 1140. But in the other situations, you have to consider 2 combination numbers, of course. For the cardinal number of B, it will be C22 times C61. So it's a coincidence here, but this result is the same on the first one. Again, it's a coincidence. The cardinal number of C is then, and I hope it begins to be clear, C21 times C62. You want to choose 1 consonant in 20 consonants and 2 vowels in 6 vowels. Result 300. And the cardinal number of D is C20 times C63. C20 equals 1. The important number here is C63, that equals 20. you will be able to check the result. If you add the four numbers, you obtain 2,600, the total cardinal number of omega, of course. Okay, thank you to have listened to this video till the end, and I will be happy to answer your questions coming from this document or the document of exercises, of course. Bye bye, see you next time.